In this lecture, I am going to start the design of shaft carrying pulleys. In the case of design of shaft carrying pulleys, the shaft is subjected to both bending and twisting movement. So first, we will start with the design procedure, then we will go into the problems. So here I have considered two pulleys. A simply supported shaft is carrying the two pulleys, pulley A and pulley B. The pulley A has vertical belt drive and the pulley B has horizontal belt drive. Okay, so because of the pulley, a transverse load will be acting on the shaft, and that is the reason for the bending stress. So we will start from the calculation of load for pulley A. We know that the shaft is transmitting some power. So the power P is equal to 2 pi nt divided by 60. So in the case of pulley A, power A, okay, because in some cases the pulley A will receive the power from a motor and it will deliver the power to some other machineries through pulley B. So if both the pulleys are transmitting same amount of power, then there is no problem. But if the pulley A is receiving a total power of maybe 20 kilonewton, the pulley B will deliver 10 kilonewton. Maybe if we have another pulley, then that pulley C will deliver the remaining 10 kilonewton. So in the case of different powers, then we have to use PA, PB and PC. Okay, so we will use PA. PA is equal to 2 pi n mt divided by 60. So P is power, N is speed. If you substitute power and speed, you will get torque in Newton meter. Further, the MTA, that is torque on pulley A, is equal to T1 minus T2 into RA. So here T1 and T2 are the tight side and slack side tension. Then RA is the radius of the pulley A. In the problem, they will specify the radius. So we can substitute the value of torque and the radius. Further, we know that the tension ratio T1 by T2, that is tight side divided by slack side, is equal to e power mu theta. Here mu is the coefficient of friction, theta is the angle of contact. In most of the problems, they will give the mu and theta values, or otherwise they will directly give the tension ratio. Maybe 2 or 2.5 they will directly give. If in the problem, if it is not given, then you can assume a T1 by T2 ratio of 2. So if it is not given, you can assume a ratio of 2. So you can substitute the ratio in the previous equation and you can calculate the T1 and T2. Then similarly for pulley B, and for pulley B, then we have to use PB and we have to calculate T3 and T4, because you can see the drawing. The pulley A, it is T1 and T2. For pulley B, it is T3 and T4. Okay. So after calculating load, then you have to draw the load diagram. Okay. So the pulley is supported on two supports. We can name it A, B, C and D. Okay. Then the supports are RC and here it is RD. Okay. So first consider pulley A. So there is no horizontal component in pulley A. Since the pulley is a vertical drive, the belt drive is a vertical drive and there is no horizontal component is here. So you can take the horizontal load as 0. And for vertical load, you just add the tensions, that is T1 and T2. If the self weight of the pulley is given, then you have to consider the weight also. Okay. So in the case of vertical load, it is T1 plus T2 plus W if the weight of the pulley is given. So if the weight is not given, then you can neglect this W. Then coming to the pulley B. So the pulley B is a horizontal belt drive. So the horizontal load is equal to T3 plus T4. You just add the tension. Remember that pulley A is a vertical belt drive. So that is why T1 plus T2 comes in the vertical direction. In pulley B, it's a horizontal drive. That is why T3 and T4 in the horizontal direction. Then if the pulley B has some weight, we know that the self weight will always act in the vertical direction. So you can consider the vertical load as W if the if the self weight of the pulley is given in the problem. If it is not given, then you can neglect this vertical component. Okay. So you can construct the load drawing. So first one is horizontal loading. Okay. So you just consider the horizontal loading alone. It is RCH and RDH in the case of horizontal loading. So there is no horizontal load on pulley A. You can see that. Then in the pulley B, the horizontal loading is T3 plus T4. So the horizontal loading is T3 plus T4. Okay. Then coming to the vertical loading, in pulley A, the vertical load is T1 plus T2 plus W. Then in the case of pulley B, the vertical load is W. Okay. So and the reactions are RC vertical and RD vertical. Okay. So this is your horizontal and vertical loading. So this is the first step, calculation of load. Then the second step is calculation of bending moment. Okay. So using the horizontal loading, you can draw the horizontal bending moment. So by considering the horizontal load, you can draw horizontal bending moment. Then by considering the vertical loading, you can draw the vertical bending moment. We know how to draw the bending moment diagram for a simply supported beam. Then by combining the horizontal and vertical bending moment, we have to draw the equivalent bending moment. So I'll tell you how to draw the equivalent bending moment diagram. From the equivalent bending moment drawing, you have to take the maximum bending moment. So MB max. Okay. So we know that in the equation of combined bending and torsion, we have to substitute MB and MT values. Okay. So the MD value is the maximum bending moment. You can take the maximum bending moment from the equivalent bending moment drawing. Then the next one is calculation of torque. So we have already calculated the torque in the first step. So you can take the maximum torque. Okay. So you can take the maximum torque value, MT value from the step 1. And the last step is calculation of diameter. So we know the equation for combined bending and torsion is d cube is equal to 16 divided by pi into tau allowable root of kb mb square plus kt mt square. So this is the maximum bending moment. This mb should be selected from the equivalent bending moment drawing, and this mt is the maximum torque transmitted. Okay. So tau allowable is the material property. If the material property is given in the problem, then you can take that. If it is not given, then you can assume any one of the material and you can select the material property from PhD data book page number 1.9 and you can substitute it here. So finally, after calculating the diameter, you can refer PhD data book page number 7.20 and by using the R20 series, you can standardize the calculated diameter. So this is the procedure for designing the shaft when it is subjected to both bending and twisting moment. So we'll go into the problem. We'll start with the simple one. A MS shaft rotating at 720 rpm, N is given, is supported between two bearings. So it's a simply supported beam, 80 centimeter apart. So the overall length is 80 centimeter, that is 800 mm. It carries two pulleys A and B at a distance of 30 centimeter and 60 centimeter from the left bearing. You can refer the drawing. It carries two pulleys A and B at a distance of 30 centimeter and 60 centimeter. You can convert it into mm. 10 kilowatt of power is fed into the pulley A with a diameter of 40 centimeter. Okay. So 10 kilowatt of power is fed into the pulley A. That is, the pulley A receives power and it has a diameter of 40 centimeter. So P is given. Then the diameter of pulley A, dA, is given and taken out at pulley B with a diameter of 30 mm. So the pulley B delivers the power. Okay, so the pulley B is actually delivering the power to some other machines. So pulley A is receiving the power and pulley A is delivering the power. Pulley B is delivering the power. So the diameter of pulley B is 30 centimeter by vertical belt drive. So both the pulleys are vertical one, having same ratio of driving tensions as 2.5. So T1 by T2 that is equal to, yeah, you can see that. So T1 by T2 is equal to T3 by T4 is equal to 2.5 because both the drives have same tension ratio. Assuming the permissible shear stress as 45 megapascal, design the shaft. So the material property is given, the tau allowable is given as 45 megapascal, that is 45 Newton per mm square. Design the shaft means we have to find out the diameter of the shaft. Okay. So first step, you just construct a simple drawing. So from the given question, so this is the constructed drawing. The shaft is a simply supported one, so I have considered two reactions, that is RC and RD. So you can name it. Then the pulley A is a vertical one, the pulley B is also a vertical one. So for pulley A, I have considered T1 and T2 as tensions. Then for pulley B, it is T3 and T4. Then you can mark the distance between pulleys and the bearing. Okay, so it is 300 mm, 300 mm and 200 mm. Okay, so this is the first drawing. Now we will go into the design procedure. We know that the first step is calculation of load as we discussed earlier. So first consider the pulley A alone. Okay, so PA, in the problem it is clearly mentioned that the pulley A receives the power and the pulley B delivers the power. So PA and P is same, that is 10 kilowatt. Okay, just a minute. Yeah, in the problem it is clearly mentioned that 10 kilowatt of power is fed into pulley A and it is taken out at pulley B. So both the powers are equal. So you can substitute that. So PA is equal to 2 pi N. N is given in the problem. It is 720 MT divided by 60. So the MT value will be 133 Newton meter. I have converted it into Newton mm. That is 133 into 10 power 3 Newton mm. Further, to calculate the tension, the first equation is MTA is equal to T1 minus T2 into RA. MTA we have calculated. You can substitute that. Keep T1 minus T2. And in the problem, the diameter is actually given. The diameter of pulley A is given as 40 centimeter, that is 400 mm. So the radius is half of the diameter, it is 200 mm. So you can substitute that. Further, we know that the tension ratio is equal to T1 by T2. It is given in the problem as 2.5. Okay, and T1 is equal to 2.5 times of T2. You can substitute this ratio in the previous equation. Substitute T1 as 2.5 T2. So in this equation, the only unknown value is T2. So by solving this equation, you can calculate T2 is equal to 443 Newton. Now you can substitute the T2 value in this ratio and you can calculate the value of T1, that is T1 is equal to 2.5 times of T2. So the T1 is equal to 1108 Newton. So this is the load acting at pulley A. And in the problem, the weight of the pulley is not given, so you can neglect the W value since the weight of the pulley is not given. Then similarly, we have to calculate the load for pulley B also. Okay, so both the pulleys are subjected to same amount of power, so the torque will be equal. So MTB is same as MTA, that is 133 into 10 power 3 Newton meter. Then the first equation is MTB is equal to T3 minus T4. In the case of pulley A, it is T1 minus T2. Here it is T3 minus T4. T3 minus T4 into RB. Okay, the radius of the pulley B. In the problem, the diameter of the pulley B is given. From that, we can calculate the radius. We can substitute that T3 minus T4 into 150. And the second step is tension ratio. That is T3 by T4. It is equal to 2.5. So in the problem, it is given as T1 by T2. That is equal to T3 by T4, that is equal to 2.5. So further, T3 is equal to 2.5 times of the T4. Okay, so you can substitute this in the previous equation and you can calculate the value of T4, that is 591 Newton. Then you can substitute the T4 value in this ratio and you can calculate the T3 value. T3 is equal to 1478 Newton. Okay, so now we have calculated the loads. We can draw the load drawing. So in the problem, for pulley A, there is no horizontal load since the belt drive is a vertical one and there is no self weight. So the horizontal load is 0, and for vertical load it is, for pulley A it is T1 plus T2. You can add the tension values, so that is equal to 1551 Newton. In the case of pulley B, there is no horizontal load since the belt is acting in the vertical direction. So vertical load is equal to T3 plus T4. That is very important. Okay. So T3 plus T4, that is equal to 2069 Newton. Now you can draw the vertical loading. You don't need to draw the horizontal loading since there is no horizontal loads are acting. So if there is no horizontal loads on pulley A and pulley B, then you can neglect the horizontal load drawing. You can draw the vertical loading. Okay. So here it is R C H reaction V. It is RC V. Then here it is RD vertical. Then the load acting, vertical load acting at pulley A is 1551 Newton. Then at pulley B is 2069 Newton. So this is the horizontal loading. Now the second step is calculation of bending moment. Okay. So there is no horizontal bending moment, only vertical bending moment is there. So it is RC and RD. So you can use RCV and RDV. So we have to draw the vertical bending moment drawing alone. Don't need to draw the horizontal bending moment. So this is the vertical load. So first step, we have to calculate the reaction force. Total upward force is equal to total downward force. So these calculations, you may be familiar with this. So RC plus RD is equal to 1551 plus 2069, that is equal to 3614 Newton. Further, moment about the left extreme point, that is moment about C, is equal to 0. So 0 is equal to, the 1551 is acting in the clockwise direction, so I have considered minus, and the perpendicular distance is 300 mm from the point C. Remember that when you calculate the bending moment, you have to take the perpendicular distance about the point. So it is 1551 into 300 since the distance is 300. Then the RD is acting in the counterclockwise direction, so it is positive, so plus RD, and the perpendicular distance is 300 plus 300 plus 200, that is 800. Then the 2069 is acting in the clockwise direction, so minus 2069 into the perpendicular distance is 300 into 300. Okay, it is 600. So by solving this equation, you can calculate RD is equal to 2133 Newton. You can substitute this in the previous equation and you can calculate RA is equal to 1487 Newton. So now we have calculated the RD and RA. Now then we can calculate the bending moment at A and B, because we know that the bending moment at C and D is equal to 0. So first we will calculate MBA. Okay, so MBA, consider the forces acting on the right hand side. Okay, two forces are acting, one is RD and another one is 2069. The RD is acting in the counterclockwise direction, so consider plus RD into the perpendicular distance from RD to point A, it is 300 plus 200, it is 500. Then the 2069 is acting in the clockwise direction, so consider negative 2069, and the perpendicular distance, so this is actually 300, it is not 600, it is 300. So it is the distance between A and B, it is 300. So if you solve this, you will get 446.1 into 10 power 3 Newton mm. Then the bending moment at point B. Okay, so this is the point B, and if you consider the right side, only one force is acting, RD. RD is acting in the counterclockwise direction, so RD into the perpendicular distance is 200 mm. So you will get 426.6 into 10 power 3 Newton mm. So we have calculated the bending moment. If you have vertical and horizontal bending moment, then you have to draw the equivalent bending moment. If there is no horizontal component, then vertical bending moment itself, it is enough. You can take the maximum bending moment value. So you can draw the bending moment drawing. In the drawing, if you see that, then the maximum bending moment is 446.1 into 10 power 3 Newton meter. This is our MB maximum. Okay. Then the third step is calculation of torque. In the problem, in the first step, we have already calculated the torque is equal to, MT is equal to 133 into 10 power 3 Newton mm. We have calculated in the first step. The last step is calculation of diameter. So you write the equation d cube is equal to 16 divided by pi into tau allowable kb mb square plus kt mt square. There is no loading conditions are given, so we can assume kb and kt values as 1, and you can substitute that. The tau value is given in the problem, it is 45. You can substitute that. mb is the maximum bending moment from the bending moment drawing, that is 446.1 into 10 power 3 Newton mm. Then mt we have calculated, it is 133 into 10 power 3. You can substitute that. If you solve this equation, finally you will get d is equal to 37.5 mm. Okay. Further, by using the R20 series, you can standardize the diameter. So the standard diameter is equal to d is equal to 40 mm. Okay. So the first step is calculation of load. So for pulley A we have to calculate the load, and for pulley B we have to calculate the load. Then the second step is calculation of bending moment. If there is no horizontal component, then you can neglect the horizontal loading and horizontal bending moment. You can calculate the vertical bending moment and take the maximum bending moment value from the bending moment drawing. Then the third step is calculation of torque. Take the maximum torque from the step 1. So in this case, both the pulleys are transmitting same amount of torque, so I have considered that. Then the last step is calculation of diameter. In the problem the tau value is given, so you can directly substitute that and you can find the diameter. So finally you have to calculate the standard diameter. Okay. So try to draw all the loading and bending moment drawing on a same page. Okay. So allot a separate page for drawing the loading and bending moment. Okay. So in the presentation I have splitted that, but in your note you don't need to split that. You just draw in a single page. Okay. So this is the tutorial problem. A shaft is supported by two bearings 1 meter apart. The overall length is 1 meter. The drawing is given. You can refer that. A 600 mm diameter pulley is mounted at a distance of 300 mm to the right of the left hand bearing. So a 600 meter pulley, consider this as pulley A. It is mounted at a distance of 0.3 meter, that is 300 mm to the right of the left hand bearing, and receives a power of 35.5 kilowatt at 960 rpm. The P and N values are given. Another pulley of 400 mm diameter is placed 200 mm to the left of the right hand bearing. So this is pulley B. The diameter of pulley B is given. It is placed 200 mm to the left of the right hand bearing, and it delivers power vertically downwards. So the pulley A is actually receiving the power from a pulley below it. Below it means it is acting on the vertical direction. So this is pulley A is a vertical drive. So T1 and T2 will be acting in the vertical direction, and the pulley B is also delivers the power vertically downwards. So the T3 and T4 will be acting in the downwards direction. Okay, so both the drives are vertical drive. There will be no horizontal component, so you can neglect the horizontal loading and horizontal bending moment, and you can take the maximum bending moment from the vertical bending moment drawing. The angle of contact of both the pulleys is 180 degree and mu is equal to 0.27. So the theta and mu values are given. So remember that. So these values are useful for calculating the tension ratios. Determine the suitable diameter for a solid shaft allowing working stress of 42 megapascal in shear for material of shaft. So tau allowable is given, permissible or allowable stress is given, so you can directly take that. Okay, so it is almost like the previous problem. Both the pulleys are driving in the vertical direction and the shaft is a simply supported one, so you can follow the same procedure, but only difference is in the previous problem the tension ratios are directly given, but here they have given the mu and theta values. Okay, so T1 by T2 is equal to T3 by T4 is equal to e power mu theta, that we have already discussed in the procedure, and mu is given as 0.24, and we have to substitute the theta value in radian. So if you convert 180 degree into radian, then you will get pi. So e power 0.24 into pi, that is equal to 2.125. So the tension ratio first you have to calculate, and you can use this tension ratio for calculating the tensions of the pulleys. Okay, so this is how you have to solve the problem.